Numbers are a pretty foundational tool in our study and understanding of mathematics because numbers allow us to do something that is really difficult to achieve without using numbers. Namely, they allow us to precisely describe quantities. That is, if we're just using qualitative measurements for comparing or for stating how much stuff we've got, we're not always going to be able to give precise formulations. The difference between the amount of tea in this cup and the amount of tea in that cup, as opposed to the difference between cup B and cup C, it gets pretty hairy trying to describe exact quantities without the help of numbers. So numbers have been around for a while. We theorize that first common human usage of numbers would have been to take stock, would have been to take inventory of possessions, whether it be livestock, land boundaries, just stuff around the house. But we can do a lot more with numbers than just count stuff. Because while, yes, we do use numbers to keep precise track of exactly how much stuff we've got where, another very important function of numbers is that they have an existence of themselves in a way that have no relation to the objects that we are counting using numbers. For instance, 2 rocks and 2 rocks combine together to give you 4 rocks, but then 2 people and 2 people also combine together to give you 4 people. The addition relation between number 2 and the number 2 to produce the number 4 seems to be almost independent of what the exact objects are that you are counting, that you are counting with those numbers. When you go deeper into the study of mathematics, you'll come to realize that we can talk about collections of sets and ideas such as greater than or less than. We'll talk about distances, and we'll talk about all sorts of things that you can describe using some idea of numbers, but that don't necessarily rely on precisely counting out objects in order to operate. So numbers have their own separate existence of their own, and the relations between the different numbers in that realm, the way numbers behave relative to each other according to the axioms of mathematics, allow us to describe patterns and ideas in the world around us in a way that we just would not be able to do if we did not have the number line. So to represent the idea of quantities on either side of a neutral point, profit and loss, debt and solvency, increases versus decreases, distances to the left, distances to the right, distances above a certain point, distances below a certain point, speeding up, slowing down, and so on and so forth. We use numbers of 2 different varieties, left and right of a center point. This center point on the number line is denoted by the number 0, which corresponds to perfectly neutral, that is nothing either way. So you can think of that as corresponding to no quantity, you can think of that as no change, and what exactly it represents, of course, is completely dependent on the exact problem that you're applying the number line to, but you can think of 0 as the neutral point. It is the middle, it is the center of the number line, and all numbers lie to one side or the other side. If the numbers to the left of 0, we call those the negative numbers. We put a little minus sign in front of those numbers. Numbers that are to the right of 0, we call them positive numbers, and we put little plus signs in front of them to denote that they are inside positive numbers. However, if you ever see a number that doesn't have a sign in front of it, which happens all the time, then you are simply to go ahead and assume that's a positive number. By convention, if a number has no sign in front of it, you can assume a nice safe plus sign. So basic introductions out of the way. Let's talk about the first type of relation that we're going to look at between numbers. That is the comparison relation, greater than or less than. How do you determine whether or not one number is greater than less than another number? At first, you might be inclined to say, well, that's surely easy enough. Right? If you've just got more stuff, the number is bigger. If you've got less stuff, the number is smaller. How hard can that be? Well, you see, we've got this whole business with negative numbers as well not to worry about. So if I've got a really big debt, is that number a bigger number or a smaller number than a tiny profit? And some people would say, well, the number itself is much bigger. If you're $1 million in debt, that's a lot of debt. As opposed to if you just if you've got $10 to your name and you don't owe anybody anything, hey, you're a lot richer than the guy who's $10 million in debt. But at the same time, you might also be saying, yeah, but 10 million is just so much more than 10. 10 million is such a big number. So how do you make sense of these? When in a world with positive and negative numbers, how do you make sense of greater than or less than relations? And the answer is, well, with the simple metric that we use is, are you to the right or the left on the number line. If you've got two numbers and you're trying to compare them, and the first number that you're going to call a number A is to the right of number B, then number A is bigger. If number B is to the right of number A, number B is bigger. If number A is to the left of number B, number A is smaller. And if they both lie on the same spot on the number line, then of course they represent the same quantity. So quantities on the number line, you can think of them as measuring out quantities from the center point 0. If you are 10 million in debt and you want to represent debt on the positive side of the world, and you want to represent profits using the negative numbers, then a profit of $10 would be represented using little negative 10, and then a debt of $10 million, you'd represent that using 10 million over on the positive side of the world. So this massive distance, 10 million, you might be saying, well, yeah, sure, 10 million is a much bigger number than 10, but still, debt that guy has a lot less money. So you're performing here a comparison not between the sizes 10 and 10 million, you're rather performing comparison between where they are on the number line. You're saying, well, this guy is in debt, that guy is in profit, therefore it doesn't matter what the size of the debt and what the size of the profits are. The guy who doesn't have the debt is just in a better spot. But then you might also be saying, well, the number 10 million is bigger than the number 10. And when you want to talk about a number, just the quantity it represents, just its magnitude, nothing to do with the side of the number line that it's on, just want to talk about the magnitude. Under those circumstances, we look at something called the absolute value of a number, and the absolute value of a number is just how far that number's position is from the center point. How far away is it from that middle, and what quantity does that distance represent? So you represent that like so. You have little absolute value bars, we call them, like these little vertical bars around a number, and basically that value is always positive, and all it represents is the distance, specifically the distance between that point and the number 0. So the absolute value doesn't really care about which side of 0 you're on, it's just trying to tell us how big the number is. Now, of course, not all numbers, not all quantities represented on the number line are entire units. The number line, part of the reason we use the number line is because it has this massive array of distances. You can be, you can be at 0, you can be at 1, but then you can also be right here between 0 and 1. You could be right there between 1 and 2, and so on and so forth. There are infinitely many possible positions between any two of these little numbers. You can decide to stop anywhere along the way. If you want, you can decide to break up this bit between 0 and 1 into a million different pieces and then stop at the 5th way station. Or you might want to break it up into 10 million pieces and then stop at the 5,967th way station along the way. Point being, the number line can represent all sorts of entire distances and partial distances, and don't necessarily have to be constrained but to numbers that exist at these units. Numbers that you can describe using entire units are called integers. Numbers 0 and above, they're the whole numbers. The natural numbers, the counting numbers, are the numbers that we use everyday objects to count everyday objects, like 1, 2, 3, 4, and so on. So the positive integers. But you've got this whole world of partial bits where instead of going the entire distance, you go part of the way. And we'll look at in future lessons, we'll look at how exactly to describe those little partial numbers, to describe those partial distances. For now, recognize that such numbers are expressed using expressed in something called a fraction, where the fraction is just attempting to demonstrate. The fraction is simply attempting to demonstrate that this number is not just composed of entire units. You go a certain number of units, and then the next unit you break it up into a bunch of parts, and then you go a certain number of those parts instead of going the entire way. A number that can be, any number that can be represented as a fraction is called a rational number. But of course, all integers are therefore by default rational numbers, because if you've got the number 2, then you can take each piece, right? You can take each unit, the unit 1 and the unit 2, and you can break it up into 5 pieces each, and then you have 10 pieces, each of size 1/5. And then you'd be able to write the number 2 as the fraction 10 over 5. So all integers are by default rational. This means are there irrational numbers? And we'll get back to ranges in just a bit. Yes, indeed, there are irrational numbers. There are numbers that is literally impossible for you to write them as exact fractions. It is possible to demonstrate that there are numbers without fractional equivalent forms. The square root of 2, that is the number that multiplies by itself to give you the answer 2, is one such number, and we'll demonstrate in a later video why this is so. But the idea is essentially, you know how we talked about in fractions, you can think about going a certain part of the next distance. Instead of going the entire unit, you break up the unit into a certain set number of pieces, and then you go that amount. Well, for an irrational number, that process doesn't stop. Let's say you go from 1 to 2. And then instead of going from 2 to 3, you break up that distance into 10 pieces, and you go 3/10 of the way. So you've covered a distance of 2 units, and then 3/10. So it's 2.3. But then instead of going from 2.3 to 2.4, you then break up the distance between 3 to 4 into 10 more pieces, and you go a certain number more, and so on and so forth, and you keep continuing forever. Every single time you have to go a certain distance to the next unit. Instead of covering that entire distance, you break up that distance into a whole bunch of smaller pieces, and therefore you end up with this infinitely extending, really long decimal number that doesn't recur with no fixed pattern, but it just keeps going, and it keeps going, and it keeps going, and it keeps going. So numbers like that, numbers which cannot be expressed as finite fractions, are called irrational numbers, and we'll look at them more in time to come. But for now, all I want you to recognize is this number whose position we can't exactly precisely using a fraction pinpoint. They're still contained within the number line. Like, we know that an irrational number between 2.3 and 2.4 is still somewhere between 2.3 and 2.4. And if we wanted to approximate its value for use in a calculation that didn't particularly care about accuracy, then we could use a rounded value of 2.3 or 2.4 to perform our calculations using that irrational number to represent that quantity, even if not exactly accurately. So, and again, we'll come back to the ideas of rounding and precision and accuracy later on. But again, I just want you to recognize for now that these irrational numbers, even though they might be weird and we might not be able to depict them as fractions, they're still very much there on the number line. The number line includes all the rational and irrational numbers that exist in the whole wide world. Now, one last thing, talking about bounds and ranges within a number line, this is basically how we would depict range in a number line. You just go from the place you want to go, you put a little dot at the place that you want to stop, and that's that. A filled endpoint indicates that this bit is included in your range, so here -1 is included in this range, but -6 is not. You could go ahead and write it like so. You could go ahead and write a range of -1 in the following fashion. You could go ahead and say, this range between -1 and range of -1 between -1 and -6. You could go ahead and say, well, that's -1 included. So to include, you do these braces right there. Those brackets right there, and then 6. We're not including 6, so you use this parenthesis right there to indicate that 6 is not included. Now, some ranges, of course, go all over the way. For instance, if I ask you, if I want to make a profit of at least 5,000, how many people have to attend my show? Well, you tell me at least 500 people. Then if any number greater than 510, I'm going to make a profit. There's no upper limit to that number. So under those circumstances, and I'm sorry I couldn't come up with a better example on the fly, I really am. We were looking at, so 500 is our lower bound. We need at least 500, including 500. If 500 people do show up, then I do meet my target of 1,000. So square brackets there, but then there's an upper bound, so this just goes up all the way to infinity. This just, any number above this is fine. But of course, infinity is not a number that I can just plug into my profit calculation machine. Infinity is just not a number, and you can't really include it in a range. You're saying, how many people can come to the show? Infinitely many. Not quite. So infinity is not something we ever include in our ranges as an actual number. So whenever you have a range going all the way, you depict it with a little arrow in the end. So you've got a range starting from wherever. You put a little arrow on the end to indicate that it goes on forever, and when you want to write it using brackets or parentheses or whatever, then instead of using brackets at the end, you use parentheses to indicate that the end point of infinity, because of course you're not ever ending, you just keep going, is not included in your range. That concludes our brief introductory look at the number line. Next up, we'll take a look at how exactly we came up with the system that we have come up with, 1, 2, 3, 4, 5, 6, 7, 8, 9, how we can use it to describe all the quantities that we can think of, and why the system works and how to describe any number using it. See you then.